Everybody seems ready. You're 1 minute early, but. All right, the first things I have to say actually are more administrative, so I'll go ahead and start. But let's talk a little bit about how the logistics are going to go in the next week, yeah? I'm excited to see what everybody's, well, I've been seeing a little bit about what everybody's working on, but I'm excited to see the presentation. So the way it works, some of you took manipulation last semester, so know roughly how it goes. But the way it works is you have a video submission, right? The videos are going to be on YouTube, right? There's a hard deadline, is Tuesday at noon. That's about how much time I've learned I need to make sure everything gets onto a slide and gets organized in time for class. So it's pretty tough on me if it's after that. Okay, so we're going to have a sheet where you just drop in a link to your YouTube video for the presentation. You will have the option to upload a public video, show all your friends, or to upload an unlisted video and put the link in. So everybody in the class will be able to see, but we won't share more broadly than that. The default, I will assume, if your video is public, then you would very much like it to be shown in class. If it's unlisted, then you're okay being at the bottom of the list, because there's a chance we won't get through all the videos. Certainly we won't get through all the videos in the first hour and a half. So, and the second thing is I will do my best, although it's a little hard logistically, I will do my best to look in the room and see who's here and play the videos of the people that are here, okay? I've got the room booked for extra time afterwards. It's a fun sort of viewing party, right? And so I'll stick around as long as it takes to see the people who are here to watch their videos. And I'd love for people to stay as long as you're excited to stay. But there's nothing I can do about, it doesn't make sense to have any possible extension beyond the presentation, right? The written assignment is due Tuesday at midnight, which is, 11:59, maybe. I've had someone call me on that before. Okay. That is the last minute that I can possibly, by rule at MIT, allow you to have something due in the class, since the class doesn't have a final exam. I'm not allowed to move it past that. If you ask for an extension, I am sympathetic to the idea that people are working hard and stressed out and everything like this. I can't extend it arbitrarily far, but send me an email if that is a huge source of stress for you. I can't officially move the deadline. Okay. Yes, so please come on Tuesday. It's really fun, I think. I mean, I learned a ton out of watching what worked and what didn't work. I learned as much about what didn't work sometimes. And I think it's just a really good way to sort of get a pulse for how well these tools actually work, what kind of problems you could have tried. Any questions on that sort of logistics? We'll make a post with those details. A lot of the details are already on the project page to be found, but maybe you haven't looked at it in a while. But we'll set up the spreadsheet that you can submit your data, your link on, and have all those details posted soon. All right. Okay, so last time we talked about output feedback, which I would love to have spent a lot more time on that. I think it's such an important problem. We've been saying that for years. Actually, that's one of the reasons, I don't know if you remember me saying this earlier, but one of the reasons I kind of switched from working on walking robots to working on manipulation is because I think the connection to perception is one of the biggest challenges for control right now. And you get that more immediately in the world of manipulation right now than you do it. Of course, you need that for locomotion too, but you can sort of always write a slightly better state estimator buy a slightly more expensive IMU. And for years I was saying, output feedback's really important. It's going to be important, but you could always do a little bit better. And then when you switch to manipulation and someone says, I'm going to roll dough, there's no buying a better IMU for that. Okay. So what were the big takeaways from the output feedback? The first thing I hope you heard was that there are actually good tools from control. There's, let's call it model-based control. Certainly, the linear system is, we understand the case where it's easy. We understand the cases where it's hard. We know a lot about why it's hard, when it's hard. Okay, and then there's natural extensions of those linear system ideas into the nonlinear space. Some of them, I think, have not been explored as much as their importance would suggest they should have been explored. But I think it's also fair to say that so far, model-based control by itself has largely failed to address control from cameras. And one of the things we've seen over the last few years is just how big of a mistake that was and how valuable it is to have a high rate feedback loop coming directly from pixels, right? And so that's where the behavior cloning and other learning-based control is currently at the forefront because of the value of cameras and rich tactile sensors and other things like this. I've mentioned, I've made these probably frustratingly side glances about reinforcement learning all semester, but I definitely tried to emphasize that behavior cloning is what's winning, I think, today in the interesting manipulation space that I was showing you. So for things like this, the rolling dough, the picking up noodles, these were both picked because if I think about with my sort of state space model-based control hat on, right, it's just very hard to think about how I would write. I mean, even if I have the model, a perfect model of the dough, for instance, and it has some finite parameterization that describes its state, maybe it's an FEM model, right, so the finite element model, right, or a bunch of almonds or something. Even if I had that state and I had a perfect simulation, asking my sensors to recover that state in order to make a control decision is just a failed task, okay? So these were all picked specifically to try to do things that I thought our typical model-based control was not good at doing, right? And I mean, even more similarly, the sauce, like what's the state of the sauce, right? But I want to be careful because I don't, so I say BC is winning at this kind of task, okay? It doesn't solve every task. It would be extremely hard to use behavior cloning to swing up an Acrobat. I've tried like teleoping an Acrobat. It's really, really hard to even get close to the swing up, let alone balance. Okay, so to some extent, let me pause this so that it is less mesmerizing. Yeah. To some extent, those problems from a controls perspective are easy, right? They are visually rich, visually complex, but in terms of like how much control authority does your control system have in its ability to affect the world, any challenges of stability, these are all easy problems, right? So you don't actually need that much dynamics thinking to be successful in this task. You need a really good perception system, okay? And teleop is sufficient to sort of get your way through that. It'd be very hard to teleop Atlas doing a backflip, right? Although that'd be kind of fun to try, right? There's things where, or stabilizing a fighter jet, right? There are things where control and dynamics reasoning really matters, okay? But I think some of the things that have been hard for control are actually easy control problems, but hard sensors. And that's where we're seeing BC have a huge impact. Okay, but that stuff does really make you think. Like you just think, okay, we've got to, and we'll review at the end of the hour here, but sort of the kind of things we've talked about over the semester. But it does kind of make you think, like how does this live, where does this live in the pantheon of control approaches, and how do I put this together with other stuff, right? Even more so, it kind of makes you think, what if I was going to make a robot that could do a lot of things in the kitchen, right? What does that look like? Our ambitions for control have grown a little bit, I'd say. Like, the word cognitive architecture is always a little scary to me, but it's kind of, we're almost ready for that conversation, I think. You know, so like, what would it mean to be a system that had many potential control skills, if you will, that were turned on and off to accomplish many tasks through the day, so how do you take all of these ideas that we've been putting out there and build them into something bigger that's not just solving swing up for the acrobat, but is somehow able to do many tasks. Okay, and that's actually the kind of the technical nugget I want to give you today. Let me give you sort of one approach, which is not the one I'll spend most of the time on. So when we did a lot of skills on this robot, and this was just a robot that could load the dishwasher, but very robustly. And the individual skills were actually pretty complicated. They had, you had to like dig in and slide your fingers between plates and pick them up robustly. You had to reorient mugs in order to get them in the sink. The way that worked was we had a lot of skills, if you will. They were mostly designed sometimes with reinforcement learning, sometimes a lot of them were hand designed. This was a number of years ago. Okay, but then we built a library of these skills that we put together. They looked like, open the dishwasher door or close the dishwasher door. And we manually articulated each of those skills, what feedback controller would run during each of those skills, and we would annotate it with basically a function that would look at the estimated state of the world and decide, yes, can I run the open dishwasher skill right now or not? So we had kind of a precondition, and then we said, if I did open the dishwasher, what would my logical state of the state here is not the pixels of all the mugs. The state here was just the task state of like, is the dishwasher door closed or is it open? Are there mugs in the sink or are there not mugs in the sink? They were a very abstracted version of that. Okay, so we built this architecture around each of these skills. And then given that logical abstraction, hand-designed logical abstraction, we could, this is just a little bit deeper view into that logical abstraction. We could make a planning solution that would look at the logical series of actions that it needed to take, that would take the initial state, the goal state, set of actions, and just plan a discrete plan through it. I would say this is the way that people had been thinking about multi-step complicated controllers being put together, right? And strips is the old way to specify it. These days, you'd probably use PDIDL. Cool kids call it PDIDL, yeah? Maybe PDDL, but I think PDIDL's better, which is just maybe a rich generalization of strips, okay? And if you take a class on task planning or task and motion planning, you'll think a lot about these kind of tools. Maybe or maybe not, depending on who you ask. Maybe those are all irrelevant now because you just ask ChatGPT, how do I do these things, and it'll give you a series of actions. I don't think it completely wipes away task planning, but I think it's surprisingly good. Surprisingly good, right? So this is another approach, right, if I can ask some omniscient friend, what actions should I take? And I have many different controllers. Tell me which actions to take at which time. And I think that's actually super valuable. The Code as Policies is one of my favorite versions of that, but there's many out there now. But I want to talk about feedback, right? So if you have good planners, good reliable planners, then one way you can try to get robustness is by just replanning fast enough. That's the MPC idea. People do it in high-level planning, they do it in low-level planning. The way we got more robust at the sort of task level in the dish loading project. Someone comes in, Boston Dynamics does like this to their robot, right? It's not quite as cool to use a rod and close the dish rack, but that was our attempt to channel those perturbations, yeah? And the robot's kind of like, oh, that's annoying, and it puts the mug back down, and it goes and races the disk rack out. Okay, it was a very robust system. You could go in and mess with it. You could throw new objects in. It would always get the job done, pretty much. And that robustness came from every time it took an action or at some relatively low rate, it would rerun the entire task planning. And you get some level of robustness from that. And that's really the MPC view of the world, okay? But, let's see if I can, I'll leave it here because that's the least distracting, okay? But there's another view of that. And that's what I really want to talk about today is sort of the controls view of how you put these things together. Because there's really a beautiful idea there that you might not have heard that I think builds on everything we've talked about over the semester and is kind of the controls version of that. So the same way, MPC is a feedback controller if I have a planner that's strong enough. But the challenges with MPC are typically, can you guarantee that the planner is going to always succeed, right? If you're running nonlinear optimization and you're a little annoyed at it today, then you would maybe feel a little suspicious about the fact that if I put in whatever new state it is, I'm hoping Dorcol is going to succeed, right? That seems a little scary. It's harder at the task level, right? Is there even a path? It's not, the planners are strong if they're discrete and logical, but you could get yourself into a situation where there's no path to success. And it's very hard when the feedback controller understudy is a planner, then it's very hard to do like analysis and sort of certify that the system's robustly stable from all initial conditions, for instance. Okay, but controls has some ways that we can do that. All right, so the way I want to tell you that story is actually goes back to one of the first, I would say, in robotics at least, to my knowledge, one of the first examples of people wanting to do multitask control, okay, with something that's kind of dynamics and control, but multitask. And it started off with this humble beginnings, if you will. This is a juggling robot. It turns out it's easier to juggle if you are on an air hockey table, and you're basically now a 2D juggler instead of a 3D juggler. And then you can just be a paddle, and that works really well. This was already the 2-ball case is more interesting than the 1-ball case. But they started doing, so they have a control system. I'll tell you a little bit about that because it's kind of a neat example. They have a control system that stabilizes the juggling. But they also have variants of that control system that can do different things. For instance, it can do a palm, right? Or it can throw, or it could, I think it was probably trying to do something like this, but in practice it was like someone brought a bar in and it just juggled on this side of the bar and this side of the bar, right? Okay, so a very dynamics and control thing, constrained to the lab, but it had a bunch of skills that it could do, and they wanted to think about how do you compose those skills into interesting sequences of tasks. Okay, let me just tell you a little bit, since you haven't heard about juggling yet, and it's just such a good, clean example that sort of captures, it's like all of the things we've talked about in class. So it turns out that the simplest model of juggling is actually just, if you have a paddle, it's actually just moving in one dimension, and you have a ball in one dimension, okay? And it turns out your state then, the way that they initially analyzed this is Kodacek and Buehler and Rizzi eventually. Al Rizzi is he's one of the leads at the Boston Dynamics AI Institute. It's kind of a different world, but same person, yeah. I guess I called this R here. So, and this, the location of this B. So if we imagine we just have immediate velocity control of the paddle, and we want to regulate the height of the ball, okay? Then it turns out, juggling is a nice periodic behavior. What do? We try to think about the system on the return map. we do the apex to apex map. Okay, so you try to take when the velocity equals 0, I'll take a sample of this and try to pick a control action that will, at the next apex, get me to the desired hopping height. Okay, this is actually the reason that Dan Kodacek got interested in juggling, is he thought this was a good way to describe Mark Rabert's hopping robots. It was a simpler version of the hopping robots. Okay, we still have if I remove b dot, I still have 2 degrees of freedom, and potentially if I've got r as an entire trajectory between those two, somehow I want to reduce things down so I get a nice, clean, ideally one-dimensional return map. Okay. The brilliant trick is something called the mirror law. It turns out that a very nice way to juggle and reduce the dimensionality is you have, this is like r equals 0, b equals 0. And if you say that the command, the space of controllers that I want to search over is just a negative scaling, basically r dot equals negative k b dot, with potentially some extra terms to regulate, you can get yourself in a situation where basically the ball and the paddle will meet at this line, and every time the ball bounces up, the paddle will just mirror, but at some scaling, the trajectory of the ball. Okay, that drops the dimensionality completely. I know that I'm going to have collisions here. The dynamics get simpler, and I just search over basically the magnitude of that scaling. Then you get a beautiful unimodal return map. So it has a nice fixed point at the stable hopping height. You can change the parameter k and change the hopping height, and you get all the return map analysis. Everything works. It's a beautiful example. The way they then extended that to 2D, it turns out the mirror law works again if you just go to 2D. So now I've got a ball here. It can move in x and y, and I've got just a rotation here. Again, if you can come up with the law that gets you to meet exactly at level, then to regulate hopping height, you can just change the k, the rate at which you're, the gain at which you're meeting the ball in order to propel it higher or lower. And then to regulate x and y, if you meet just a little bit earlier or a little bit later, then that will push the ball either way. And so a simple 1 degree of freedom planar thing with a mirror law gave beautiful good controllers for 2D, and then 3D followed like this. And they worked really hard on these controllers, and they understood roughly their regions of attraction. Certainly in the approximate models, they had unimodal maps. They had sense of the region of attraction. And then they started building variants of it, like palming and the like. And they said, how do I put all that together? I did all this hard work to build a nice control system. Can I leverage that? And this was the first time, this is, I guess, the 2-ball case I forgot to show, but good stuff, yeah. Okay, this is the first time I saw this picture, was their paper, Burridge, Rizzi, and Kodacek. It's a famous one now. And the title was Sequential Composition of Dynamically Dexterous Robot Behaviors. Right? And the words that they used were that the Lyapunov function is a funnel. We should think about a Lyapunov function if we have for our system. We should think about that as a funnel, something that takes a large set of initial conditions, and through control drives it to a smaller set of conditions. And then the picture that they gave was, that can be it doesn't have to be a nice circle, right? But we have some ideal funnel that might capture a huge range of initial conditions from lots of different states. Maybe that's like the biggest one you could possibly find. But if you have these smaller, simpler funnels, then maybe you can do sequential composition by thinking about sequencing funnels. Okay. So in fact, Lyapunov functions become exactly the tool that you need to do that strips-like combination of skills in a more continuous domain, right? If the precondition of whether you can execute a skill is whether you're in the inside the region of attraction, let's say, of a controller, then that's, yes, I can execute that skill. And even if you want to plan further into the future, then thinking about simulating your Lyapunov function forward into some smaller set, does the output of this Lyapunov function lead into the inlet of another one? That means I can compose the skills sequentially in time. It's a very beautiful idea, I think. And ideally, if you do it right, maybe a bunch of simple skills can sort of cover a huge range of initial conditions, right? So maybe this is like every recipe that you want to execute in the kitchen or something like this, and you have a lot of different skills, right? The space would be much more abstract in that setting, but the idea maybe is sort of similar, that composition of these skills could be exactly what you would need to make a richer library of control. If you contrast that with the MPC approach would say I'm in one place. First of all, the MPC approach would probably be thinking about single trajectories, not these funnels, okay? But that would be thinking about sort of trying to drive me from this initial condition down here, and it's very hard to certify these planning type controllers. If I have built this huge library of Lyapunov functions, I actually have a Lyapunov function that's, the composition of those is also a Lyapunov function, and it covers a huge range of initial conditions. So I have some confidence that not only that I have some stability guarantees, but I also have some sense of coverage maybe of like how you could imagine being done in this setting, for instance, right? You could imagine having enough controllers and saying, I've solved this problem. There are no more initial conditions where I'm outside of any Lyapunov function. Yeah?
How well does this scale with dimension?
That depends on your sums of squares power or whatever. I mean, I think that depends. So yeah, I think the questions about when we did sums of squares, regions of attraction analysis, how does that scale, would be exactly the questions to answer this. You're talking about you're talking about cursive dimensionality kind of thing. Yeah.
Yeah, the number of funnels you would need.
Yeah. I mean, everything's a little weirder in high dimensions, but I think we're not taking out points, we're taking out volumes, right? The question is, do those volumes get relatively smaller in high dimensions, or do we get proportionally big regions of attraction in higher dimensions? Yeah.
Did they propose, so if you have all these overlapping funnels and you have like a starting condition that you want to start at an ending condition, did they propose a planner to navigate through all the different funnels?
So the specific thing that they proposed was that you give a total ordering of the funnels, because when you do this, you have to be careful, for instance, that you don't chatter between funnels and stuff like that. One of the questions is, if I'm in the inlet of multiple funnels, then you don't want to risk going back and forth. So they actually, in the simplest version, had just a total ordering, and they would, instead of planning, they would just simulate forward, basically. And they would go down, they would execute that funnel until they dropped out of it into the next one. And as soon as you would always execute the highest priority funnel, and that would take you down the chute into the goal. Yes?
How do they generate that priority between funnels?
I think that was pretty hand-baked. Yeah. I should say the funnels were fairly hand-baked too. This was before we had good tools for regions of attraction, right? So even the funnels were empirically designed by doing a lot of trial and error. But it's awesome. But now we can just solve those, for instance, given a model or a robust model and all these things. That's basically what I think. I think they had the idea right. They just didn't have enough tools back in the day. So you revisit this now with some newer tools, and you can do a lot of cool stuff, right? This was their picture of trying to someone put a bar there and they wanted to juggle over to the other side, where they had to do a high pass and then go under, and they were composing Lyapunov functions for that. So it turns out, so that, like I said, that was the first time I saw it, or I saw it in that way, at least. I don't remember which order I read the papers, but the first time that idea really lit me up, thinking about dynamic controllers being composed with Lyapunov functions, was the Burrage and Rizzi paper. But they credit Matt Mason, for instance. Matt Mason credits Mark Rabert, but Mark says, yeah, I don't know what he's talking about. So everybody was very generous, I think, back in the day. But this certainly, like Matt Mason and Tomás Lozano Perez, some of you know Tomás very well, they had this idea too, even earlier, in thinking about just kinematic planning. These are snapshots of a picture of how you might do a peg and hole insertion. And they thought about the pre-image of certain actions that if you were to just take, like, say, straight line, simple primitives kind of things, where could you execute that? Where would be viable places to start executing that? And they had a notion of pre-image backchaining in the kinematic planning world that really was sort of a precursor to that type of idea. Okay, so one of the things I did when I was younger was try to take the Burrage and Rizzi thing and use all the new tools, right? And this is kind of how it plays out now, given all the tools you've seen in class. Okay, so let's say we wanted to solve the global feedback controller to swing up the pendulum. Well, not because it's the hardest problem, but just because it fits on the screen, right? So for instance, just take out the toolbox. We've got a fixed point we want to stabilize at the top. First thing you do is you linearize the system, call LQR, compute the region of attraction of the LQR controller. I chose particularly weak limits for that to be a nice small controller, just to make the point, okay? Now, we want to build funnels that go into that. So you can't linearize around arbitrary points. What are we to do? Well, we can linearize around trajectories. So now take the whole line of thinking we've done with trajectory optimization and sample-based planning, and let's try to put that together into a basic recipe. Pick a point at random in the state space. If it's outside the funnel, then we have work to do. Try to design a trajectory, use trajectory optimization to try to design a trajectory. It doesn't even have to get to the goal. It just has to get back into the gray regions. Okay? I found a trajectory. And then you can compute the time-varying LQR controller, the time-varying region of, it's a region of attraction because it does have it dumps into the final time invariant controller, so it's a region of attraction because it has infinite horizon stability, right? And actually, the way that the sums of squares program goes, I can write down some of the details of this, but the final conditions, it's actually doing backward reachability. So the final conditions is that I have some ellipsoid here, and I'm trying to grow backwards towards here, the biggest funnel that is going to certify that if I start anywhere inside this funnel, and I follow that controller, that it'll end inside that funnel. Yeah?
How do you optimize for a biggest one?
Well, so the time invariant one we know. This one, if you remember the basic conditions of this, was we have our parameters were rho. So we're going to do some scalar level set of the Riccati proposed cross to go. So we have x transpose s of t x. Okay, and we want to I'll write it down. So in this case, we're going to solve for the Riccati equation and call S fixed. And the search becomes just over rho. And we just use as a surrogate, bigger rho is bigger volume, which is pretty good, right? I mean, yeah. So we would just try to push up on rho and crawl backwards from the goal to find the biggest rho that can stay inside the funnel. And then this was in the age of MATLAB animations. I did this one. Pretty good, right? Let's do that one more time. Okay. But you can see where that's going, right? So if I just take that recipe, there was nothing, I mean, I used the 0, 0 as the initial sample just because that's an important one, but there's nothing special about that sample. Pick another point at random, and you can start growing until you fill the space, right? So the recipe there, I mentioned it a little bit in the trajectory optimization, or sorry, in the sample-based planning. The recipe there was, if you find a place that was unoccupied and you solve a small trajectory optimization problem, it was, you have an initial condition that's fixed, that was your random sample. You have the dynamics of the plant, and the final condition is not to get back all the way up there. It's to get anywhere back onto the tree of existing solutions, okay? And so you can write that. It's a slightly ugly constraint to write. It has branching logic in it, where basically you say, given, I mean, you could think about the add constraint that you would write in mathematical program, for instance. You'd say, given my current guess x, what is the closest place on the tree? The distance between that x and the closest place on the tree should be 0. And that has the effect that if it's, you know, kind of close, if it starts off being close to 1, it'll sort of snap to that 1. It can even walk along the tree in order to satisfy the constraints, walk back up another branch. Huge difference in terms of connecting, you know, the number of successful connections goes way up if you do that. So that's kind of cool. What it gives you is the ability to extend some of the notions of probabilistic completeness in a sample-based planner to, we called it probabilistic feedback coverage, right? So if this is the region of interest, this sort of cyan region, this was a system that was constructed intentionally to have a known limit to the region of attraction. Like it cannot recover from initial conditions outside here, and the goal is here. So we know the region of attraction is going to be on this side, and we say the region of interest, the sampling region is the cyan. Then what you would expect is that as you add more samples, then your set of possible initial conditions that are guaranteed to work grows, and in the limit it will cover the entire true region of attraction of the system. Yeah?
Is there anything interesting you can do in like how you sample those points?
For sure, I'm sure, yeah. You have some ideas? Yeah, we tried a couple, I mean, some of the simple things. I mean, I think all the sampling heuristics we talked about for dynamical systems are still relevant here, right? Because this, what you want is to have a high probability that when you use the trajectory optimization, you get a successful connection. Yeah, I think better sampling distributions would only help. The total ordering here, so you asked, so how did we get the ordering for the initial one? Here the ordering is simple because the tree actually constructs the order, right? So you actually have a parent-child relationship with the other elements in the tree. So the order which you execute is preordained, and when you're executing, you just stay in the funnel until you drop out the back.
Do you find a difference in like what the coverage looks like if you grow sort of backwards from the goal to try and cover the space versus selecting random points in the state space and trying to grow to the goal?
So in the standard sample-based planning, you would typically grow in both directions, the bidirectional, like RRT, for instance. We always thought of this as going backwards from the goal, where we had some initial controller. Sorry, in this version, we actually, I'll tell you about the online version of it in a second, but yeah, in this version I thought about the problem of stabilizing a fixed point with the biggest possible region of attraction. So it was starting with the fixed point and growing backwards. And then everywhere, you know that every one of them will eventually get to the goal. Yeah?
Since this is a tree, do you ever have an issue where like you have to traverse nodes that aren't necessary and you end up having like a problem?
Okay, good. Yeah, so in what sense is this a good controller, right? So the trajectory optimization, you'd think would be locally optimal, but not globally optimal, right? So a composition of these is not necessarily a globally optimal path. The controller is locally optimal to the trajectory, but is not globally optimal on the space. So I think there's like reasons to be optimistic because there's local optimality in a couple places, but it's definitely not claiming to be a globally optimal controller in any way. This is more about robustness or guarantees of getting there. Yeah.
If you added rewiring in like RT style, could you get probabilistically optimal?
Yeah, we never did that. The timing of that, I guess, was we just never did that. Yeah, it's a good idea. I haven't thought through that. Yeah. Cool. There's a bunch of details here, right? Remember when we talked about the sums of squares funnels? So for instance, the result of a trajectory optimization is a piecewise polynomial. It is not actually dynamically feasible to arbitrary degree. If you start integrating back your sums of squares conditions, it will very quickly say there is no controller, or there is no certification because it converges not to the trajectory you solved for, it converges to something nearby. So in practice, we were often leaving out a little tube in the middle and just saying that it converges to very close to allow for a little window of numerical approximation in the middle. Contraction metrics have come up as a way that you could potentially give a certificate that doesn't have to know where the fixed point is, right? There's versions of that could work too. Lots of interesting numerical details sort of hidden inside there. So this was my favorite cart pole video. So when the very first time that I showed you guys the cart pole, I showed this video and I said, don't ignore the LQR trees part, but now you understand the LQR trees part, right? So this is actually just a very robust controller. It can handle the hard limits, that some of the approaches based on more smooth analysis or more, this sort of joint limits can be painful for some approaches, but for instance, like the energy shaping controller wouldn't naturally handle those. Yeah, and it just works nice and robustly. This is also, in fact, the project that encouraged all this line of thinking was actually the Perching plane project. So again, I told you about this. I even showed this picture saying we designed trajectories, we computed regions of attraction. But in practice, the way we got from it landed on the perch once or twice to it almost always landed on the perch is we built a library of funnels that we're all trying to get back and get to the goal. And we got to the point where Joe could throw it on every throw and get to the perch. Like this. Oh, that's his whole thing. Sorry, wrong video. Okay, how would you think about that for walking robots, right? So I actually think it's a very natural way to think about walking robots. Okay, so remember we have limit cycles of a compass gate robot. The region of attraction is well defined to a limit cycle. It's going to be a periodic Lyapunov function that guarantees convergence to the limit cycle. We get it with the transverse coordinates. We have a hybrid limit cycle, so we have a jump periodic Riccati equation, and we have the regions of attraction that are, doing all the right things around that. And then what does it look like if you start filling the space? Sorry to walk around some more, right? Now this is giving us our kind of recovery maneuvers. So if you're knocked far off the trajectory, off the nominal limit cycle, then this could be like the woohoo, get back to the controller, and you could even have some that take multiple steps to recover. But eventually, as you fill out the space, you become robust to many initial conditions. Yeah, so to Tommy's question, the time when we stopped thinking about doing it backwards from the goal and started thinking about doing it forwards from the current state You could take the backwards reachability sums of squares and do a forwards reachability sums of squares. And this is very connected to the tube MPC we talked about, for instance. Okay, so in practice, we made a library of trajectories that would sort of do fly straight and bank and straighten out, make a small but rich library of trajectories. And each one of those, we'd compute the biggest funnel, given some choice of an initial ellipse. We try to make it as big as possible going forward in time now, and say these are the possible places that I could end up. Okay, but we have a Lyapunov certificate. Now at runtime, so we do that without any obstacles, like Emilio did with his RRT planner, right? So we do a lot of computation of the vehicle without any obstacles. Now we're faced with new obstacles, and we can quickly check all the funnels and ask if they're going to intersect, and pick one that doesn't. Even a little bit more clever, since a sub-level set of a Lyapunov function is still a Lyapunov function, we don't just have one funnel for each of those. We can shrink our funnels and immediately have, if we have to get through a tighter corridor, we can start with a tighter set of initial conditions that will guarantee to go through there. Right, so this would be the shrinking operation. We got an initial funnel there. We solve a small optimization that guaranteed that these initial conditions would not collide. Again, the amount of work that went into making that video of it flying through the funnel from MATLAB was significant, so I'm going to play it one more time. That was Ani's work, not my work, but he worked really hard on that. Yeah?
Is there a reason why the regions are increasing in size as time increases? Like, you would assume that if you have a protracted controller, it gets smaller.
Yeah, so I think when I said it, so you can, okay. First of all, noise makes you go out, stability makes you go in, right? So both of those things can happen, right? And yeah, you would typically actually want your funnels to be more convergent for planning too. So I said push out on the end. I think you actually want to push out at the beginning and have it be a funnel, yeah.
So like you have noise when you're constructing.
If you have noise, then it can push out, yeah. And we would typically try to do the robust version of that, yeah. The other thing you have to do in your, well, this was one of the first motion capture sort of stuff everybody was doing. Motion capture changed what we could do with our vehicles, but we were still afraid of putting real obstacles in, so we did synthetic obstacles for a little while. And then by the end, we're doing real obstacles once we were sure and proud. And the obligatory last obstacle is always, oh, come on. What's it going to be? You guys guess the last obstacle? Has to be an MIT. Yeah. And we flew, Ani flew a lot of those trajectories. And we had certificates. We would check the sums of squares certificate. I mean, of course, there's a model. Everything's a model. We built robust versions of that model. It was like very high percentage stayed inside those funnels. I think we clipped one wing once or something like that. It was a very successful experiment, I would say. Yeah.
How do these approaches deal with, say, like those videos of like a falcon like flying through a forest?
Yeah.
And it like folds its wings in and
Yeah.
folds them out again. So one where you're actually changing the morphology of the robot to avoid an obstacle and still to be able to continue flying and things like that. Can this deal with that? And
Yeah, that's good. So when we were doing this project, we were working with the Harvard Field Station. Andy Bewinter and his lab at the Harvard Field Station are awesome. They're just great collaborators. They were flying pigeons through similar obstacles, and they put cameras on their heads and motion capture markers on their wings, and you'd knock the pigeon off one perch, and it would fly through the poles to the other perch. And I kept saying, like, can we get a goshawk? Like, goshawks are awesome. There's like all these videos online of them going through, he's like, well, pigeons are really good. You know, I never got a goshawk, but I do think those goshawks are awesome. I could probably even dig it up if you haven't seen. There's videos of like, you know, super high res, slow motion of a goshawk flying up, and it like goes through a tube that's almost smaller than its body with, apparently at almost full speed. You know, and it's like even using its talons to push out the other side. It's just the epitome of grace, right? And our planes have these wings that they can't really. That was one of the annoying things. The pigeons would be able to go through cases where we couldn't because they would just fold their wings, or they would bash into it and they wouldn't care because their wings are robust, and our planes would just go down to the ground. Or they would thrust vector like crazy because, so, you know, we started that project thinking I will understand the optimal decision making of the pigeon, which when I say it that way, that just sounds like a bad idea. But we were trying to, you know, understand the control system in the birds, right? And the answer is they're not optimal. They're really not optimal. So, and you know, we were trying to say like maybe they're maximizing distance or like probability of collision, or you know, we had all these hypotheses. And then finally one day they put like poles on the right side of the lab and like no poles on the other side, and there was still a 50% chance of them flying through the poles. We're like, okay, it's not optimal. I'm giving up, you know. But one of the reasons for that, I think, is because they have so much thrust vectoring power. What we did learn was that they basically didn't start thinking about that. You could sort of see, because you could watch, we had a head tracker on them, and they don't foveate with their eyes. So if you look at where their head's gazing, you know where they're looking. And you could see them kind of like fly along and then like, oh, there's something, and then, and they would do it like within like less than a meter for sure at fairly high speeds. So they're just flying along, and they just know they can get out of the way of almost anything, and it hits it. And our planes are like reasoning way back in the distance. None of that answered your question. Sorry for that. Yeah, so the state space of the goshawk would include the wings in ways that our planes typically don't. The obstacles would be in the configuration space. They'd be harder to visualize. But everything else should work. I really think that the pictures we've drawn are still approachable for that problem. I mean, you have to ask how well you can model the dynamics of your goshawk and all these things, but the approach works. No one else is going to ask a question now. You get a long answer. Okay. Good. Yeah, so I think the algorithm is clear enough. I don't need to write it down. So let's just maybe have that high level discussion. I think people had enough appetite for it last time when I was talking about, you know, foundation models for control and things like this. That I think maybe let's just discuss that for a minute. Okay. So what's wrong with this? Like, why doesn't that solve everything? I kind of acted like it solved everything. It doesn't solve everything. The biggest reason for me is that it's a state feedback controller. The output feedback matters, right? You can't assume that you can estimate the state, or even that you know the state, or that the state dimension stays meaningfully constant over the course of your, right? There's more complexity hiding out there. Now, output feedback, we could do output feedback motion planning. It's a great name. Glenn, who's in my group, wrote a paper about that before. But I think that's a very powerful paradigm. People are doing things like that when they're trying to talk about skill composition with learned controllers, for instance. So you could learn the initiation set now, try to say, when does this controller succeed, when does it fail, right? And then try to build up something a little bit like this. But I do think there's principles from the Lyapunov and the like that are stronger than what people typically apply in the learning control setting so far. The state space, so just to be clear, assuming that you have a state space model is not bad. Assuming you can estimate the state and you're making control decisions based on full state information, that's what's bad. Right? So given our conversation last time, having a state space representation, that just means you have like an RNN, or a recurrent network or something. And the state space of your harder tasks should be interpreted probably not as the every link of the noodles on the salad. Okay, it should be something like an approximate belief, compressed belief space, some approximately sufficient history of your previous actions and observations that is good enough to make decisions, control decisions going forward. That notion of state is great. It goes the distance, right? And so, you know, funnels should look like something like these, I think, Lyapunov-like functions in these learned representations potentially. I think there's a lot of ways you could go with that. I think the compositionality, I currently would say it matters, but this is a big open question, right? So is the foundation model for control going to be something that asks a large language model and then composes lots of small feedback controllers that were trained for individual skills? Or do we just have one big policy in one massive transformer that takes whatever image and whatever natural language instruction and gives me the torques? I don't know. We're going to find out. It's probably not either one of those, actually. I would guess it's somewhere in between. Probably more hierarchical and modular or something like that, if I had to put my money down. But maybe not. Maybe it should just, I mean, it seems like current evidence is suggesting that one massive thing is going to win the race. What do you think? Yeah. Yeah.
Just kind of a more general question, but I mean, right now, like vision is used for feedback a lot. But do you ever, I mean, what is that a limitation in of itself? Like, if we don't use vision, we use touch, for sensing. Will that kind of change the architecture that we want to design?
Yeah. So how important is the role of vision? I think we underestimated how important the role of vision was. I remember when I started really using it more, first depth cameras came out, and we're like, oh, this is great. We can use cameras, but we can still think of them as like a Euclidean distance measurement. That was great. And then at some point, I remember the day where I was like, I asked Pete and Lucas, I was like, okay, if you could keep either the depth channel or the RGB channel, but you can only have one, which one do you keep? They said, give me the RGB. It's so much more informative than the depth. There's so many cues that we have when we're manipulating the world that are coming from the RGB, that if you only had one, and they were, clearly that has played out. Like that's just so many, you can get everything from RGB nowadays. But that was a big switch for me because I thought, I underestimated the role of cameras, I think. The tactile sensors, the richest tactile sensors today, tend to have cameras in them, right? So the visual tactile sensors are the ones that are most popular these days. Put a camera underneath your skin and watch the deformation. So I do think that's a huge part of the pipeline. I don't think it means you have to throw away models. I think the representations you get out of pixels can be grounded in the kind of state spaces we're used to working with.
If there were to be a robotics foundation model, do you think it would be somehow platform agnostic, or we would have like a foundational robot that everyone uses that is determined to be the best?
Right, so the question is, would the foundation model for robotics be platform agnostic? People debate about this. I would be tickled already if someone gave me a EWA WSG foundation model, right? And if they got a Panda, then I'll have to get a different foundation model. I would already be super impressed. So even if the long-term thing is that you have one model that works for all the robots, I would lean in personally. I think it's more important to think about just doing all the skills with one robot first. And if that helps us with data efficiency or whatever, I would take that path. But I think the true believers want one model that rules them all, right? That you could change number of legs, number of arms, and it should just figure it out. I don't know if there's any natural intelligence that can do that. I mean, you can put ski boots on and stuff, but that's pretty different than like gaining an arm. I don't know. It seems like you'd have to relearn a little bit. Yeah.
Just building off of that, if you have a policy that works within like a certain amount of, let's say, joints, and then you were to lose one of those joints for some reason, is there anything you can say about like how that policy would now perform in a reduced dimension, even of just the same robot?
well, let's take the tools from class to address that. So let's say my walking robot lost a leg or something. Maybe let's start with more than 4 legs, just to, so it's not, otherwise the answer is it won't work. I think you could think about that as a particular, losing a leg or freezing a leg could be viewed as a constraint that you've added to the problem that wasn't there before, and you could ask what the set of solutions you've already analyzed do subject to that constraint. I think there's hope for analyzing that. I think, adding constraints or losing degrees of freedom feels a little more approachable. It's still changing the model significantly, so it depends if your original model could even be predictive in that case. But these are the good questions. I mean, so almost everything I've said all year was there's a state space. It has dimension, n, right? But that's not probably how the models I use when I'm going through the world. They're much more flexible than that, right? So I can kind of dial into the state of my head, and I wasn't even thinking about that at all a minute ago. So somehow that state became relevant, and it wasn't relevant a minute ago. And somehow we need to have a much more, I think, dynamics-based metacognition, as sometimes people will call it, about understanding what our models are, how they change, what our planners are doing. Probably we have planners. I would think it's not just memorization, but again, that's almost a religious argument at this point.
Yeah, so just kind of think in that vein, I'm used to, you look at something with a camera, you construct a model of what you're seeing, and then you can reason within the model. And then a lot of this sounds like behavior cloning is going to essentially a high version of optical flow, where you don't really care about what you're seeing, you just care about I don't even know how to.
No, I understand your point.
Some meaning that you infer from the image and the way it moves. How do you bridge the two and have some model-based reasoning or inference without constructing the full model, but without just being optical flow?
No, I mean, people have proposals about this. I won't maybe say the whole thing, but how do you bridge this sort of, Oh, so by the way, the optic flow example is one of the big things that made me start thinking about output feedback more generally. Because even before we had, super awesome computer vision, I worked really hard to compute funnels for these airplanes, and it's like a pretty complicated thing. And then someone could go, and we were trying to fly through forests or whatever, and then someone came along with an optic flow feedback controller that wrote like 4 lines of code on a Pixhawk, and like it just, the pixel's going that way, then I'll go that way. And it did it like almost as well, So that was a moment for me. I was like, well, there's something not quite right about all this work I'm doing for something. So I think that's a great example, by the way. If I knew the answer, I would have told you, and I'd be very famous. but I think that's one of the big questions of the day is how do you combine all these things? How do you have these flexible models? I mean, when the modular neural network work was coming out, that felt very natural to me. Of like you have different, it came out with visual question answering systems and stuff first, and people have strong opinions about that for various reasons, but something like that feels very natural to me. Like you maybe have modules that are turning on and turning off, maybe not even discretely. I would be happy to discuss it at more length, but yeah.
I guess like in terms of like the state of the art of this sort of like general purpose control, like what's the order of magnitude of like computational requirements for this kind of stuff? And like is there like a vision where it's like on the same horsepower magnitude as like brains?
I see. So the question is about amount of computation. So I think the learning side of the world is using ridiculous amounts of computation right now. I mean, you get maybe something out at the end that's a small amount of computation, which is satisfying, but the RL certainly uses a ridiculous amount, but even training and diffusion policy, it's like on the cloud for a night, doing work in order to train those things. You could compute sums of squares, a lot of sums of squares funnels in that amount of time. That was another thing that was, if you just want me to tell you all the times I was surprised and disappointed with myself. Right, I was like, we're working so hard to make optimization problems and feeling bad when they like ran in more than a minute, right? And then suddenly it was okay to train there was a while where people were training these even just vision networks for like months. I'm like, wait, if that's the rules of the game, I would have done different things. You know, if you're allowed to spend that much time. But that's come down so fast. So, and if people talk about cloud compute, I mean, maybe your robot is going to be just an edge node on a what should I call it? A hive mind, right? Fleet learning is something I'm very excited about, actually. So you had a question back there?
So I read about liquid neural networks recently. Are you working on that at all?
Say it a little louder.
Liquid neural networks, do you work on that at all?
Daniela right next to me does, but I haven't worked on it myself.
Oh, okay.
Sorry. That's good. Okay, yeah, one more.
It seems like a lot of these very deep models we talk about have weird brittleness in certain parts of them. Like where if you use a slightly different camera, if you move the camera a little bit, they would fall apart. What are your thoughts on getting around that in the future?
More data? So the question was, you know, if you move the camera and things fall apart, then are we really building, you know, solid systems? I do think that's just a data problem. I mean, that's one approach. So of course, if you put in more structure and more bias, then you could go farther with less data. But I think that particular problem will just be overcome by data. I think that seems like a safe prediction at this point. Yeah, whoever starts training with enough different lighting conditions and bumps their cameras enough and just they can remove that assumption. And that's starting to happen already. Yeah. It used to be that, yeah, if you could always tell when people visit the lab if they're more theoretically minded or more experimentally minded. And the best indicator is if they like go up and like lean on your camera, you know they're a theorist, because no experimentalist would ever do that to you. That's just mean. That's mean. That's like you've got to recalibrate everything. Okay. I could keep going, I guess. But let me just kind of back up, and I do hope that was useful. I think it's such a dynamic time. The conversation will be completely different in 3 months. But you guys are part of it. You're in the thick of it. Let's just remember all the things that we talked about, right? So we did a lot of stuff in this class. Maybe too much, but hopefully it kind of, you know, got you thinking, right? So I really tried to start with simple systems, you know, acrobats, cart poles, pendula, right? And we got a lot out of that. And there were some pretty satisfying solutions. You know, we got the basics of optimal control. We got dynamic programming. We got Lyapunov theory. We could do sums of squares for control. We even started to do a little bit of, you know, trajectory optimization and the like in these systems. We did LQR and some of the special cases, right? That's a pretty powerful toolbox. I hope not just the specific algorithms, but just the way of thinking that it forces. I hope those ideas will serve you well in whatever, you know, simple or more complicated systems you think about. You know, we started talking about walking robots. And there was a bunch of new complexity that came with that. The most important one was the dynamics of contact. How do you do planning and control through contact? Which in most cases, we actually do have pretty nice extensions of this basic idea, at least in the case of hybrid models. Where you think about each mode separately and you try to stitch them together with careful reasoning about the intersections. And I still think that's fairly satisfying, right? Although it starts getting very hard as the number of contact modes really grow. And that's kind of led us to more discussions about humanoids and quadrupeds and higher dimensional systems. Right, so many degrees of freedom. And not all of those approaches go the distance yet, right? Trajectory optimization scales in terms of its run times, but maybe not in terms of its brittleness, right? And if you have complex, many degrees of freedom, complex obstacles, that's where I think some of the motion planning tools like sampling-based planning and ideas about simple models like centroidal dynamics, models start to play an important role, right? Remember I said when we got to humanoids, it's like it got harder. There was a little part of the problem that actually got easier when we got to humanoids because you had enough degrees of freedom that your simple models of thinking about the center of mass as a spaceship again is actually pretty good for a lot of things. And then the last part of the class was really trying to be about stochastic, robust, output feedback, all of these important extensions. And there's just so much more to riff on in that direction, right? I just feel like I barely scratched the surface. Apply it, adaptive control, I didn't really even mention. System identification, state estimation, there's so much more you could do to really do that well. And I think the connections between that and learning are just so important and so good right now. Right, so that was this year's menu, right? But I kind of like to think about where are the frontiers of this and what did I leave out and the like. I do think that, we talked about it a bit already today, if you ask me this notion of what's the state, what are the right representations, how do I turn them on and off for different tasks, this bigger notion of state representation, how do you learn state representations that are task relevant? This is really, I think, still one of the most important and kind of frontier topics in control. A lot of people, for instance, will learn a representation by, like an autoencoder, for instance. So I'll say a good representation for state is something I can take my image in, I can compress it to a small vector, and then repredict the entire image. And that's just clearly wrong, I would say, right? I mean, the things that I need to make control decisions are so much less than the ability to predict every feature of your face in order for me to write something on the board. That just doesn't seem right, right? So there are interesting notions of how do you learn task relevant states, but they're still hard. I think that's a wide open problem. Yeah. I do think controls from cameras without throwing away models is just it's just going to be better in a year or two. You come by and see me in a year, I hope I have a much better answer. We just must do that. We must do that. I don't think we shouldn't immediately have to pay a huge tax in data and compute in order to use a camera. The notions of robustness that we talked about, even when we talked about stochastic and robust, they were fairly narrow, right? So robustness to initial conditions in my known state space, robustness to model, distributions of W. I mean, you can model almost anything that way, but when I don't even know how many objects are going to be in the scene, or what the weather's going to be like tomorrow, or what room I'm going to walk into, these notions feel like they're not quite strong enough to talk about open world robustness. But they're the right basis. I think it's the right foundation. I think these tools have to grow into this problem where the state space is more flexible, the distributions are more categorical as well as continuous, right? These are super important sort of frontier areas. I mean, of course, learning plus control, I've said that over and over, I think that's an important area. Not just, I mean, in some of the technical ways that have been happening already where people are just bringing learning theory results into the control space, but I think in deeper ways, like a lot of our success in control, experimental control, is very empirical right now. It's very data-driven. You know, we showed videos, it kind of works, learning curve went like this, but I think we need more than, I mean, we will have more than that in a few years. And I think those results are exciting enough that it's brought you guys, maybe, you know, and it's brought a lot of new talent into the field. So I'm like just very optimistic that it will get better. And people appreciate, even the hardcore experimentalists, I think there was a few years in there where they were kind of like, we don't need your theory, this stuff just works. And that's gone. I think now people are like, yeah, I really want this to work better. Maybe theory is going to help. So I sense a renewed appetite for deeper understanding of things that can actually work on these systems. And I maybe just a last one to sort of riff on, but I do think this question of what is big data, fleet learning, you know, I think almost every time in the semester, I said, here's our robot, here's the control task. Let's solve it as if we just woke up this morning and didn't know anything beforehand. And that's probably not the right problem, right? If you think about, let's say, the steady state, where we have lots of really good robots out there, and they're all sharing their data, and they already have N skills, and they want to get the N+1 skill. That seems like a very different problem than start from scratch, invent a Lyapunov function or whatever. You know, I don't know. I don't have all the answers to these. These are the frontiers. But it's just such a good time for you guys to be in the field. So I hope you keep working on it. And yeah, good. That's good for me. So I will stick around and talk to anybody who wants to talk more about projects as long as you guys need it.